where we discussed that how an instruction get executed, right? And so this is the repeated kind of thing that we perform. We fetch, we decode, we execute. Then we move to the next instruction. We again fetch, we decode, and we execute. This goes in a loop forever. So your computer is built around this concept that each time any program gets loaded into the memory, step by step, it will get executed, and for which you have to fetch each of these instructions. The program gets converted into a set of instruction, and those set of instruction get executed one by one. Now, fetch execute cycle I've already discussed. Let us start from here, the organization of a register. Now, recall that we were mostly discussing about something which is called like register transfer, right? Let's say move R1 comma R2, meaning what? From R2, the content of R2 will move to the content of R1. Or let's say even add R1 comma R2. And you have also seen that for executing any of these instructions, there is an architecture. There is we discussed about single bus architecture, and through which the data from R1 through the mux comes to one input of your ALU. Data of R2 comes to another input of your ALU, and finally it gets added because add control signal is basically generated, and then the result moves to a register called Z, and from Z it goes to the bus, let's say. For all these operations we perform, we have to generate a lot of control signal. For now we will see just that for a register Ri, any register Ri, what are the things needed and what we wanted to perform. You think of a register R1 or R2. What exactly we were doing upon all these registers? Either we were loading a value into the register, isn't it? We were transferring the value if it is a move instruction. If it is a move instruction, move R1 comma R2, then we were loading certain value into R1. But if it is a add instruction R2 comma R1, then R1 is brought in from the bus to one of the register. Okay. So the idea here is that for any register that we have, there are two things that needs to be done. One is the internal bus. The data from this register must be available to the internal bus, and the data from the bus should be available to the register. Why that is needed? Can you tell me an instance where you want to transfer data from any register to the bus? Can you tell me any instruction?
Ma'am, can you please repeat the question once again?
What I'm saying is that you have a register R1, right? Okay. You want to, under what condition you want to transfer the data of R1 to the bus? Think of an instruction where you want to transfer the data from R1 to the bus. No one can tell me this?
Store word.
To store the data from R1 to some memory location, right?
Yes, ma'am.
Yeah. So anywhere, if you also wanted to do add R2 comma R1, this R1 must be available in the bus, and from this bus it will go to ALU, right? So for executing many instructions, we need to transfer the content of a register from that register into the internal bus, so that from that internal bus the data will be available to any other register as and when it is needed. But you have to understand one thing, that we need to transfer the content of this register to the internal bus. So for this instruction only, let's say an instruction add R1 comma R2. What needs to be done? The content of R1 must be available in one of the ALU input. Content of R2 must be available in another ALU input. So for performing both these operations, what do you need to do? You need to bring the data from R2 to the bus, and from that bus it will go to one of the input of the ALU. So this is basically a condition where you need to basically transfer the content of register R1 from that register into the bus, into the internal processor bus. Is this clear to all of you? Arunava, is it clear to you?
Ma'am, can you repeat?
What I'm trying to what I'm trying to say, let's say I have to execute an instruction at R1 comma R2. How will you do that? How will you do that? You have to bring the content of R1 and content of R2 into ALU. One content will be R1, another content will be R2.
Yes,
So for bringing these two content of these registers, you think of the single bus architecture that I have discussed way back. In the single bus architecture, from the content of any of the register must be available in the bus, and from the bus it will come to this R1 and R2. Clear?
yes, ma'am.
Yeah. So for bringing the data from the register to the bus, you need to bring it this way. From register it should come to the bus.
Yes, ma'am.
So for this instruction, you need something so that the content of these two registers must be brought into the bus. I will discuss about the control signal next, but you understand under what condition you need to transfer the content of a register to the internal bus. Clear now, all of you?
Yes, ma'am.
Yes, ma'am.
Okay. Now tell me a condition where you want to get the data from the bus into the register. From the bus into the register. Krishnendu, can you tell me?
When we have to write in the memory.
Not only write in the memory, whenever you have to do this instruction, move R1 comma R2. The content of R2 will move to R1. How it will move? First, the content of R2 should be available in the bus, and from the bus it will move to R1. Right? Even for the instruction add R1 comma R2. First you have to bring this data R1 and R2 into the bus, but after the addition you have to again bring the data to R1, right? In that also you have to make the data available from the bus into this register. So these are the typical condition where we need to this is a register, we need to either bring the data from the bus into the register, or we need to bring the data from the register into the bus. Is this point clear to all of you? Then I can proceed with the control signals. There are situations where you need to bring the data from the internal processor bus to your register, and at certain point of time you need to bring the data from the register to the bus. I told you the situation when you have to bring. I need an answer from you guys, then only I can proceed. Arko Jyoti, is it
Yes, ma'am.
clear? Arko Jyoti, you are not there. Tomojit, are you there?
Ma'am, Orkojyoti wrote in chat box.
Okay, Arko Jyoti wrote in chat box. Is it clear to Arko Jyoti? Can you get his answer from there? What did he wrote?
Ma'am, he wrote repeat. Please repeat.
Okay, so are you not able to understand that from a register, we have a register, we have many general purpose register, R1, R2, dot, 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 to let's say R15, let's say 16 registers we are having. What kind of operation are we performing on these registers? We are either performing add operation, any arithmetic operation, R1, R2. Either we are performing certain operation like move R1, R2. That means for the first instruction, the content of R1 and R2 must be added and it will be put in R1. And for the second instruction, the content of R2 must be transferred to R1. So for performing all these operations, I have discussed with you long back regarding single bus architecture. In a single bus architecture, the data from this register may move to the bus, or if the data is available in the bus, it can move into the register. So basically two set of operation can be performed on a single register. One is bringing the data from the register into the bus and from the bus into the register. These are the two things that can happen. I gave you an example. Please see my video after this class that where we need this. Fine. So these are the two conditions where we need this. But actually, how will we do it? For actually doing it, we need certain control signals. That means this is a register collection of flip-flops. With this, a switch is connected and a signal called R1 out is used to place the data in the register on the bus, from the register onto the bus. So from the register, if you want to bring a data into the bus, we want R1 out. Let's say the name of this register is RI. So it will be RI out. Okay?
Yes,
So
ma'am.
from the register, the data will be available into the bus, RI out. We have to activate this, we have to make this RI out as 1. Similarly, if we want data from the bus to be available into this RI register, what we need to do? We need to do RI in. RI in means the data from the bus will move into RI register. And RI out means the data from register will be available in the bus. Please clear this out. There are two things that we are doing on a register. What are the two things? The two things are either we are bringing in data from the bus into the register, and for that we need a signal RI in. Similarly, when we are transferring the data from the register into the bus, we need the signal RI out. So RI in and RI out are the two control signals that are typically used for register transfer. And the input-output lines. These lines are the input lines to the register. You think of a parallel in, parallel out register. You can parallelly input data into the register, you can parallelly output the data. In the same way, you think of this, you can parallelly in the data here into RI register, and for that, this switch, when RI in is 1, that means you can transfer the data from here to here. Otherwise, you cannot. You have to activate this signal RI in. Similarly, if you want the data from the register to be available into the bus, then you need to activate the signal RI out. Out means what? From the register to the bus. In means what? From the bus into the register. So basically, input and output lines of the register RI are connected to the bus via the controlled switches. These are the controlled switches. So the input-output lines are connected via these control switches. If you have any queries, ask me now. You are getting questions from all these topics. So please let me know if you have any concern. Shall I proceed then?
Yes, ma'am.
Yes, ma'am.
RI in, RI out. Remember, RI in means something comes into this register. RI out, from the register it is going out. Okay, let me proceed now. So now, when RI in equals to 1, I have already told you, the data available on the bus, the data that is available on the bus, whatever data is available on the bus, will now be loaded into this RI. Okay. When RI out equals to 1, when RI out equals to 1, the data from the register RI are placed onto the bus. So it will go to from this way, from the register to the bus. Clear? So if you do something like R1 out, R1 out, R2 in, what will happen? If you write these two control signals, this means that this is 1. Whenever we write a control signals, means this is 1. Rest of the control signal which is not written means they are 0. So what is the implication of this? Can somebody tell me? R1 out and R2 in at the same time? Yes? Anybody?
The content of R1 is storing in the bus, and that content is going again from the bus to R2 register.
Perfect. Very good. Very good. So this is what it is doing. Content of R1 is available onto the bus, and from the bus the content will move into R2. That means simply R1 data is moving to R2. That's it. Isn't it? Okay. If this is clear to all, let us move on with this one, which I just now told you. Now think of a scenario. This is called register transfer. Okay. Think of a scenario. There will not be one register. There will be multiple registers that will be connected to this bus. You think of MIPS architecture. There are 32 such registers. So there will be 32 such registers which will be connected to this bus. Isn't it? Now I'll show you with two examples where we say that two registers are connected. One register is R1, another register is R2. And each of the register is having two control signals. What are the two control signals? R1 in and R1 out. So R1 in will make the data from the bus to R1, and R1 out will make available the data from the register into the bus. Similarly, Same way, from the bus, if you want to come in for R2, it will be R1 in signal. And if you want the data from R2 to be available in the bus, R2 out should be there. Fine? Is it clear to all of you? Now there can be many registers which are connected. So those many registers will also have all these R1 in and R1 out. That means Ri in and Ri out. Are you convinced with this diagram? All of you?
Yes, ma'am.
Okay. So now let us see that as I told you, whenever we say that we want to transfer the data from one register to another, we basically enable the output of one of the register R2 out equals to 1 and enable the input of another register R1 in as 1 for transferring the data from R2 to R1, right? Now, this you have to understand that how these control signals will get generated. I am understanding that for this instruction, move R1, R2, we need to generate certain control signals. But how these control signals will get generated, there are methods for it that we will be looking into next. Before that, let us see all operations are performed in synchronism with the processor clock. You know there is a processor clock, and when you buy a computer, you know that your processor clock speed is, let's say, 1.9 gigahertz or something like that, right? And so on. So basically, if you see this, that what is this? This is nothing but the number of times your clock will go on and off in 1 second. That is your clock speed. So what it says is that all operations, all these operations that we are talking about will be performed in synchronism with the processor clock. Fine. So we will say that at time period T1 is 1 clock cycle, something like this will happen. At time T2, something else will happen. At time T3, something else will happen, and so on and so forth. The control signals are asserted at the start of the clock cycle. So basically, you know, this is an off period, this is an on period, and this is an off period. So this is one full period, on and off. So this is another full period. This is on period, this is off period, right? This entire is called a clock cycle. Okay, this is a clock cycle. So this could be 1 T1. Okay, so under this clock period, it says that the control signals are asserted at the start of the clock. Okay, of the clock cycle. This is one clock cycle basically. This T1 from on period and off period together constitute a clock cycle. So what it says that the control signals are asserted at the start of the clock cycle. And after the data transfer, the control signal will return to 0 again. Because I am saying that at T1, T2 0 will be on and T1 in will be on. That means these two control signals at time step T1, okay, at time interval T1, these two control signals will be 1, and rest of the control signals, let's say there are R3, R4, all controls, R3 in, R3 out, everything is 0. All other control signal will be 0. Only whatever is written here at this time period, this will be 1. Okay, and after this T1, these two control signal will again return to 0 unless and otherwise it is specified at time step T2. Is it clear or should I repeat this part?
Ma'am, clear.
Clear. Great. Shall I proceed now?
Yes, ma'am.
Devjit, Devjit, are you understanding?
Ma'am, actually, Devjit net is not working. That's
Okay,
why he
okay,
got
okay, okay,
disconnected.
okay. Let me see if there is. Okay, I see. Fine, let's proceed. Now, you already know about this architecture, right? I've discussed about this architecture and we will be doing anything based on this architecture. Fine. So whatever I discussed so far, R1 in and R1 out, you see, these are the registers which are connected here. These are the registers that are connected here. So two-way means what? Data from this register will also move in here, and from this bus it will come here. So for each of these register, R1 in is there and R1 out is there. So similarly, R0 in is there, R0 out is there for all the registers. Fine. Similarly, for MAR and MDR also, MDR, okay, there will be this sign. So for MDR also, MDR out and MDR in will be there, and so on. PC out and PC in will be there, and so on and so forth. So all the registers that are there, similarly for this Z, Z in and Z out will be there. So for all these registers, okay, there will be these control signals, and at each time step, T1, T2, Tn, these control signals, required control signals, gets generated for executing a particular instruction. Is it clear, guys? This I've already discussed. What is program counter? What are general purpose registers? What is instruction register? What is MDR and MAR? And temporary register, arithmetic and logic unit, internal processor bus, and multiplexer. You know about all these things, right? Let me very briefly say about this in one go, very quickly. Anytime you want to execute an instruction from PC, the content of PC must move to MAR, and then what we do, we activate read control signal. After the entire instruction is read from memory, it is transferred to MDR, and from MDR it goes to IR. It goes to IR, and then the instruction decoding takes place. After decoding the instruction, now whatever I was discussing, the control unit basically generates the required control signals. Now it has decoded. If it is add R1 comma R2, it knows that what kind of instruction is this. It will decode and it will understand that these two are processor registers and this control signal is add. Okay, fine. So based on this, uh, it generates the required control signals depending on this particular architecture. Whatever you are seeing here, based on this, it basically generates the control signals. I have just shown you a control signal. How do you transfer from one register to another? But for executing an entire instruction and how it works, we will be discussing about all these things in the next semester course. Fine. Now the concept of something called tri-state buffer comes into picture. I'll start this, but I want you to, can you please do the following? Perform this instruction. What kind of control signals will be needed for this? Can you do for these two? Okay, so So what kind of control signals will get generated for executing the main instruction? Okay, just do it and send it to me in WhatsApp. Okay, I'll be back in 2 minutes. Yes, guys, are you done?
Ma'am, can you show the question once again? Actually, at then
Okay,
I just
sorry. Anybody for the first instruction, can you quickly tell me what will be the result?
R5 out, R4 in.
Okay, so the data from R5 will move to R4. So R5 out, R4 in. Shobhik? Shobhik, are you there?
Yes, ma'am.
So is it clear?
Yes, ma'am.
It will be R5 out, R4 in. Okay. And for this instruction, for the next instruction?
At first R8 out.
Yes, at first you have to do R8 out. You have to then?
Then R7 out.
Yes, then you also have to do R7 out, right? And then you
Then
have to do add, right?
addition. Yes. Next
And
R7
then the
in.
value will be available. Yeah, then whatever value will be available in will be in Z, right? If you
Yes,
recall
ma'am.
this, you add some value, it will be available in Z, right?
Yes, ma'am.
Yeah, so it will be Z in first, okay? Then it will be Z out. After Z out, it will be R7 in, isn't
In.
it? Now, I'm trying to explain you this. See this. Here you have R7 and R8. Right? Now you see, you have to first do R7 out. So it will come in, let's say it will come in here. Then you have to also do R8 out, and then it will come through Y. So first will be R7 out. It may be available in ALU because it is directly connected. Okay. You can then do R8. Then you can basically, just a second. Then you can basically do R8 out and then Y in, and then you basically have to select Y such that the data from the bus, from R8 out, when you do it is available in the bus. From the bus, when you do Y in, it will be available to Y, and through this mux you have to select Y such that it is available to this ALU input. Right? So now at one of the ALU input is R8 and another ALU input is R7. Then you have to activate a signal called add. Right? Because the control signal here is add R7, R8. So you activate this add. After addition, what you have to do? You have to do Z in. After it is added, Z in. You have to also do Z in. So you can do all these operations in a single go, but we will see that in the next semester. I'm not wanting to complicate you at this point of time, this thing, but for now you understand that you need to do both R7 and R1 out such that it is available to ALU. You perform some operation and now the result will be available in Z. After the result is available in Z, you have to do Z out, and then from Z out, the data will be available in the bus. Where you have to put? It was add R7, R8. That means R7 equals to R7 plus R8. Right? Z out. Then tell me. Z
R7
out,
in.
then R7 in. Right.
R7 in.
In. Because it will go in there. Right? Using this architecture. Whatever I am discussing with you, using this architecture.
And what is the second step?
Which one?
Like R7 out and R8 out?
Yeah.
First, then
So
what is the
basically,
second step?
first step will be for this instruction, add R7, R8. You can do the first step as like this. R7 out.
R8 out.
No, out you cannot do at the same time. You see, there is only single bus. Right? When it is out, the entire content is available here. And from here, somebody can get in. Anybody can get in. Number of times in can be more, but out can be only one. Right? So
Yes, ma'am.
first you do R7 out, then Y is connected here. You do Y in. It will come to Y. Then you have to select either 4 or Y. You will do select Y, and then it is available to this input. Right? This is one step. In one step, you have to do R7 out. And with many other signals, that is Y in and select, such that it is available to one input of the ALU. Now when you do R8 out, see, if you do anything out, this is directly connected to the ALU.
Yes, ma'am.
So it is directly connected. Whatever is available here, it will be directly available here. So when you do R7 out here, in ALU, R7 was also available. So that's why, but you need R8 here, right? So you do R8 out. Once you do R8 out, that means you see in the ALU, both R7 and R8 now is available. All you need to do is activate the signal called add. You add it and then you do a Z in. Fine. So So what you did using these 3 steps, first step is R7 out, Y in, select Y such that it is available here. One of the ALU input. The data R7 is available here. Now R8. R8, again you do R8 out. Once you do R8 out, it is directly available to this ALU input. Now both R8, R7 and R8 are available. Now you can directly add. And after adding, you can also put it inside this register Zin, because through ALU it is directly connected. You also activate Zin. But you cannot do Z out now because R8 out is already available here. It will overwrite it. Right? So for that reason, in the next step, you have to do Z out, and where you have to finally put the output in R7, because Z out contains the added value of R7 and R8, which will be stored back in R7 now. So Z out and R7 in. That's it. So basically what I'm trying to say, 2 times you have to do R7 out and R7 out and R8 out in 2 steps. This will be 2 time steps. Let's say some Tn and Tn plus 1. And this will be Tn plus 2. And finally, this will be your last step. There will be many other steps that, as I told you, I'll not be discussing in this course, but in the next course. Dipankar, is it clear?
Yes, ma'am. So 3 steps.
So basically for this 3 steps for now, but I have not included the steps for fetch.
Yes, ma'am. Yes.
Right? So there will be 3 extra steps that we will be looking in later. Okay, as I told you, in the next semester. So we'll begin with this thing in the next semester. Is this clear to all of you? Others? Do you have any
Yes, ma'am.
doubt? Okay. Perfect. Now tell me one thing. That you are connecting with the bus so many registers, right? So many registers are connected, right? So many registers are connected. So you need certain control signals here to block it, such that the data, all the data are not available at the same time into the bus. And for that reason, what do you need, you know? So R1 out, R2 out, okay. The output of several registers are connected to the bus or not? Yes or no? Several outputs are connected to the bus? You see, think of the hardware, how it is connected. It's a flip-flop, right? The flip-flop input is connected here, but flip-flop output is connected, output of R1 is connected to this bus, output of R2 is connected to this bus, output of MDR is connected to the bus, output of PC is connected to the bus. So all the outputs are connected to the bus, right? But you think of the situation, exactly one register output must be enabled at a time. That is why we were doing Z out once, and all other out must be 0. R1 out must be 0. R2 out must be 0. All others should be 0. Only Z1 out will be 1 when I write in a step, let's say T1, Z out and R1 in. When I write Z out and R1 in, then Z out will be 1 and R1 in will be 1. But rest of the register, this signal, R1 out, R2 out, or any Rn out will be all 0. Right? So how in a hardware this is implemented? How to disable the other register outputs? Okay. Have you understood the problem here? If you cannot understand the problem, then the solution you will not be able to understand. I'm trying to say here is that in that internal processor bus, this one, there are many register input and output are connected. But if you see, we only need the output of one register at a time should be available in the bus. All other register output must not be available in the bus. Yes or no?
Yes, ma'am.
Because when I do R1 out, I do not want R2 out, R3 out, data will be available in the bus. But you see, these are connected. These are connected. All are connected. But we do not want the data to be available in the bus. Right? So what is generally done is that we disable their outputs to high impedance state, also called tri-state. So basically, in this state, the outputs are electrically disconnected from the bus. So what control signals we use? We use control signal like R1 out for this purpose. Again, try to understand. I am trying to say that there are number of registers that are connected to this bus. In this example, I have given two registers. One is R1 and one is R2. So the output of R1 and R2 must be connected to this bus. But at a time, I want that only one of the output of any of the register must be available in the bus. And all other register output, although it is connected, but should not be available here. How can I do that? How can I do that? When this is a wire, this is a set of lines which is connected here. Okay. I want only this may be connected at one point of time, but others is disconnected. I don't want this to be connected. I don't want for R3 it is connected. For R4 it is connected. What to do for that? How to disable other register output? We can only do this provided we have something where we can disconnect this line. But this is a wire, like a wire can have 0 and 1 line, or 0 and 1 voltage, high and low voltage. But you can also have another state, and that is performed through this digital component called Tri-State-bufer. What it does, it disables their outputs to high impedance state, also called tri-state. The outputs are electrically disconnected from the bus. So basically, the line is connected, but the value available here is such that it is just like nothing is connected here. Okay. Is it clear to you, guys?
Yes, ma'am.
Okay. Okay. So how do I do this? This is done through something called tri-state. Why we are calling it tri-state? You remember we call others as basically just a second. अच्छा जाओ जाओ Okay, okay. So what I'm saying is basically that this high impedance state is a kind of state which is electrically disconnected basically from the bus. So even if it is connected, so it will not pass any value. Okay. So that's how we implement the bus structure in computer. So let's see this tri-state buffer. This is how it is basically connected. The bus interface switch of every register state, that is flip-flop. You know, each register is nothing but a 32-bit register means there will be 32 flip-flops which is connected. So it is connected in this way. This is the bus that we were talking about, and this is, let's say, your register. So the control signal we were talking about R1 in, from the bus it will be available here. And depending on if this is 1, then the value from bus will go to this D input of your flip-flop. And you know, at every clock, if your D is something, that value will be stored in Q. Right? Similarly, the output Q is connected to this tri-state buffer. This symbol is tri-state buffer. And using this symbol, we connect the signal R1 out. What is R1 out? If R1 out, if this R1 out is 1, then the value from the Q will be available in the bus. But if R1 out is 0, then basically this is electronically disconnected. So nothing will be available in the bus. No signal will be available in the bus. Okay? So this is how in practice it is implemented. And this is basically the signal. So if you see, please see this diagram. This is a tri-state buffer. If you provide an input, and this is the enable signal and this is the output. If your input is 0, if enable signal is 0, then whatever input you give, either 0 or 1, this output will be in high impedance state, Z. High impedance state is denoted as Z. Okay, that means it is neither high nor 0. It is somewhat in the state which has got no value. Basically, if you just keep an open wire somewhere, it is just an high impedance. It is like that condition that is happening here. But similarly, if this enable signal is 1, then if the input is 0, then the output will be 0. Buffer, right? Buffer will be similarly like this. And if the input is 1, the output will be 1 if your enable signal is 1. So similarly, you see how it is implemented. This R1 out signal is connected to the enable input. And if this signal is 0, then basically this is electronically disconnected, Z. So nothing happens. So similarly, if this signal is 1, then you can say that the data from this flip-flop will be available in the bus. From the register will be available in the bus. This is all about tri-state buffer, which we use when more than one register output is connected to the same bus. Please read it from the book to understand it more clearly. Okay? Do you have any doubt here? Anybody?
No, ma'am.
No, ma'am.
Okay. Let me stop the recording.